Hello everyone. Today we are going to introduce a bit about how to use the software GenX to do polarized neutron reflectivity fitting. Okay, so the first thing we need the software GenX. So the current latest version is 2.2.0, which is also the version we are going to use. So first we double click the software. At the beginning we need to choose a model. We want to do this neutron reflectometry fitting, so we want to choose the specular NX, Neutron and X-ray. Alright, and then the next step we need to choose a configuration. We choose reflectivity. Here is it. So this is the main panel. At the beginning step we are going to import the data, but before that I'm introducing a bit about the sample. So here is the sample layer by layer. At the very bottom it is a substrate, and there are two layers. This EU is not commonly used, but it's ferromagnetic, and at the top there is a amorphous protection layer. Alright, we are going to build this one layer by layer and do the fitting. So first we want to import the data. We want to change the name here because we have polarized neutron reflectivity, so we have like two set of data, spin up and spin down, and we add another data set. Alright, and then we file import data. We choose this up data and file import the spin down, and we save it, just call it fitting. Alright, this is not so easy to look, so what we do, we change the y scale to logarithmic. Then the log scale is much easier to see. Alright, but we want to do more. Actually, we don't want them to be seen separately, so we want to be first change the plot setting. So for one, we choose the simulated data and the real data, both red. For another, change the plot setting, change them both blue. We haven't started the simulation yet, so we only see the experimental data. But now we only show one, but we have here view and use toggle show. Okay, then we can show the two set of the data and later two set of the fitting in one figure. So that's it. The next step we want to do is we want to build up the sample layers. The first on the top is ambient, so which corresponding to somewhere here, vacuum or air or anything. Alright, and the bottom we call it a substrate. In our example we use aluminum oxide, alpha aluminum oxide, which is sapphire. Online there's another example here. It uses magnesium oxide as a substrate. So the purpose, we double click, we're going to change by using this layer editor. That's pretty straightforward. We change this atomic scattering factor F, and I already copy and paste here. And we also need to change the neutron this scattering length. Alright, we don't need to input the real number, we just to introduce like a FP or this BC, just a bond coherent, right? Just need to input this because this GenX software already has a database, so just need to input this way, AL203, so BC.AL multiplied by 2 plus BC.O multiplied by 3. Exactly the same as this tutorial online. Alright, okay, the important thing we need to do is first we need to change the D, which is the thickness of the layer. Since it is substrate, we don't need to change anything about D, just say 0. And sigma is the interfacial roughness. We just say 5, and later we will optimize it automatically. This density is the important thing to change. Online, in the frequently asked question, it has a tutorial how to change this density from mass density gram per cubic centimeter to this formula unit, which is like number of scatterer per unit volume. So which is pretty straightforward. We have this density like 3.9 gram per cubic centimeter, and we also have this atomic mass unit. We just need to do some conversion. Alright, we can put the entire thing right here and click OK. Then the substrate is added, and we click Save. The rest of the thing we need to build the layer as described here. In order to achieve a better fitting, sometimes especially we know there are some interfacial difference, we build some sub-layers, which means we divide each layer by several sub-layers. For this EUS, we may have this EUS1, EUS2, or this amorphous layer. We also build 2 sub-layers. The one on the top, close to the air, may have lower density or something. But here, for illustrative purpose, we just build layers. Before building layers, we have to build the stack. The stack is used to very convenient for super lattice. It can be done in a repetitive way. We just say layers, pretty simple, but we don't need to worry about the repetition. Alright, we just build several simple layers within this stack. We can also say that each layer belongs to individual stack, but that's not necessary. So insert a new layer, AL203 top. We need to name it, and later if we want to change the name, we just click the force icon here. Then we can give a new name here. Alright, okay, so we also need to edit this layer. For this top layer, we also need to edit this scattering factor, neutron scattering length, and also we need a density, and we need some thickness, say 70. Don't worry too much, later when it optimizes, this will update it, and roughness. Alright, now this sample tab looks like this way, and we build another layer. We call it European sulfide, and also pretty simple. We just have this scattering factor using FP, and also have a neutron scattering length, and also we have this number of atoms per cubic centimeter, the density, and we know the thickness, and we can define a roughness, and it is kind of like a magnetic, so we can define the magnetism here, but later definitely this will also be updated. Alright, and finally we build this bismuth selenide, this layer, and do the same thing. Interestingly, so this layer, the sequence from top to bottom, is just the same as this sample description right here. If we make some mistake, define it on the bottom. For example, we made a mistake, European sulfide is close to the substrate. We just need to click this move up and to move it to the correct position. Just remember, all of this need to be within some stack. Alright. Okay. So layer, this one we also need to build it. Just for completeness, we just build it. Also the same way we build the other layers. And also density, we don't need even to calculate, just write down the equation how to calculate. And sigma. Alright, that's it. And the next step, we need to edit the instrument using this icon. The neutron reflectivity, usually we collect data in the not like XRD. The coordinate should be the intensity versus Q, not 2 theta. And probe, we say it's neutron polarized. Here we say it's UU, spin up. But interestingly, since we have 2 data, we will take care of this later. And resolution, we can do this convolution, and we can even using this resolution as a parameter to the fitting, so fitting could be better, have the better quality. Alright. And now we just click this flash button here. It's called simulate. Then we can do this simulate here, and we can see this blue line is just simulated data, but we don't see the red line because we don't add any magnetism here, so it's like a non-magnetic. In order to simulate them both, from here, simulations tab, and we just need to click on add, and we add the instrument, and we just need to take a look, simulations, instrument, and set polarization. So this expression should be UU, spin up. Similarly, we do it right here, instrument, set polarization, DD. Then that's the way how we do in order to set the both simultaneously. Okay, now we simulate again. We can see the blue line, it's spin up, spin down simulation, and the red line, the spin up simulation, explained here. Alright, but the simulation is not good. We don't manually change the parameters here. Instead, we go to the grip tab, and we go to the parameters. We right click, and we add the different parameters for this simulation. For example, we can add this resolution. We click fit, then it will fit like this. Alright, and we just do it in this way. We can auto insert a lot of rows, and many things need to be simulated. For example, if we have certain layer, of course its thickness and its density maybe, and also roughness, called sigma, needs to be simulated. This is the initial value extracted from here, but we can always change. It won't change here from the sample tab, but it will update right here. And this is just one example. We need to do this to all these things. And so for simplicity, I just don't want to do this fit, but instead I just show this example right here. For example, we have the substrate thickness. This is the bismuth selenite. I divide them by 2, and this European sulfide, and it's also divided by 3 because near the interface the magnetism is different. Also, the protection layer is amorphous, so we can assume there's some interlayer like a diffusion between these two layers. So we even define a layer for them both. For the interfacial regime, define a separate layer. For this aluminum oxide, we define a top because it's close to the ambient, it has different density, and also we have it here. Alright, so this is the way how we do to achieve the real simulation. And we have some initial value, minimum, maximum, and we simulate it's already good. But if we really want to fit, we click this button, start fit. Alright, start fit. It will then start the fitting, and it will calculate this figure of merit. This log, this one can be changed from settings optimizer, and we use this figure of merit using log. This I think is a reliable way. It will continuously decreasing. We can always stop it. It will ask us, do you want to keep the parameters? If we think the fitting is better, we may click yes, and we can continue the fitting. Alright, during the fitting, we can see how it changes of this figure of merit. Basically, based on different iterations, it will just gradually drop. And these are the parameters. When it close to the top, it just touches the upper bound, and when it's close to the bottom, it's close to the lower value. Alright, for example, for the parameters number 2 here, it's the density. Now we see the minimum is 0.017, so the value is pretty much close to the bottom. That's why the red dot is almost here. Alright, and if it's close to the max, it will appear right here. So this is the number 3, like this, also appear at the bottom, so because it reaches the minimum value. And so this is the scattering length density. So this 0 on the left is the substrate, and this 100 angstrom is the regime for the bismuth selenide, which is corresponding to this layer. Alright, and this one is the total scattering length density, and this one is this. We click reflectivity and click show imaginary part and auto update during the fitting. And this one is this aluminum oxide. And in order to reach the fitting, we just add different parameters and think which is physically correct, physically reasonable. For example, here we add this regime for this interdiffusion between this range and this capping layer, and we fit the different parameters, and eventually we can get something like this, which is this magnetic, and this is the total scattering length density. And we can click reflectivity and click export. Then we can output this one. And for the fitted data, the fitting is can be improved, but it's pretty good already. We can also export the fitted data like this. Alright, so here is the example. After some data processing, we can plot the beautiful figures to talk about these different layers, and we can have this different this fitting already improved, have this fitting result. Okay, so basically here is our introduction to this neutron reflectivity data. So if let's review, we do this spin up, spin down separately, but we can view them in one figure. We first build up the sample layer by layer, and this direction, if it appears at the bottom, it appears at the bottom of this real sample, and we input the parameters by right click parameters what we want to fit to this grid tab, and we input the value, just click start fit, and then the fitting will be started, and the figure of merit will decrease, and it will get the scattering length density you want. Okay, thank you for your attention, and GenX is really great to do this kind of work. Hope you can enjoy the fitting, and so that's it. Bye bye.